Hello and welcome back, beautiful people. So today what we're going to be talking about is we are going to be talking about lines of best fit. And we're going to be talking about that in relation specifically to our last video where we looked at bivariate data. So there's some sort of relationship between an X and a Y variable. So let's just start off with a quick simple example. So let's say you are someone who does maths in year 10 and you really love maths, right? So you're going to go home and you're going to do lots of study for me. Thanks, guys. I appreciate that. And so I'm going to then graph your results as a graph against how many hours that you've studied. So this is how many hours that I've studied. So let's call that study in hours. And let's say that the maximum amount of study that you've done, let's just put like 100 hours as the max, make it nice and simple. And then let's say this axis along here, that's going to be your score. So by putting this on the dependent axis, what I'm effectively saying is that your score is going to depend on the number of hours that you study. And again, let's just make this nice and simple. Let's say that this score is out of 100. So our top mark there is going to be 100. Now, if I was to ask every single person how many hours that they had studied, it's going to be a little bit different for everyone. But there is a general pattern that I have noticed, and I've mentioned to you this pattern before, and that pattern is that the people who tend to study more or who tend to come to talk to me or who do tutorials or email me on a regular basis, those also tend to be the people that do better on their exam because they step in and they say, oh, I'm having an issue with this and I want to fix that issue. So I think that that's really important. Hint, hint, if you are struggling, please email me. Okay, so let's pretend, so I've got all your scores and you've told me all the hours that you've studied. And let's say that there are some of you, you know who you are, that have not studied very much. I mean, you guys are all pretty smart, right? But we're at that stage in our lives in high school where, being smart is not enough. You have to actually do some work to get some good results. So let's say you're still operating in that year 9 mindset where you're saying, nah, I'm real smart. I don't need to study. I'm just going to do the bare minimum. Then, you're not going to do that great. And, we might have some people who haven't really studied that much, but they still might do well. They might be pretty intelligent people and they might be able to pick up on stuff pretty quick, but they're still not going to do as well as what they could have done. On the other end of that spectrum, right, like the more that people do tend to study, the score does tend to go up. Again, unless you're like some sort of super freak genius, right? So we start to see this sort of relationship between these two variables. Now, what I can do is I want to figure out some stuff. I want to make some predictions. So what I'm actually going to do is I'm going to take a line and I'm going to draw a line and I'm going to try and hit as many of these points as I possibly can. That kind of worked, sort of. And if I can't hit the points, I'm going to try and go sort of in between them. So I have about equal numbers of points on either side of this particular line. So this line here then is going to be my line of best fit. And what I can do with that is I can actually use that information now to make some predictions about people's score. So let's say that you are someone and you're like, Miss Lee, she's posted this graphic and you know what, I'm a bare minimum kind of a person and I want to know if I only study like 2 hours, how well am I going to go on my exam? What can I predict my score is going to be? And then you look at this and this is probably going to be what, like around 10%, and you think, maybe I should put in a bit more work. Now, minimum standard for a C in mathematics in Australia at the time that I'm filming this is 40% according to QCAA. So let's say, okay, well, I actually want to get a minimum of 40% so I can pass overall on my exam. How many hours of study should I do? And so we can sort of backtrack now and we can go, okay, so I probably need to be doing about 50 hours of study to get the bare minimum on my exam. Now, this is probably an over exaggeration. It's not an accurate graph, blah, 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 all of that. But it's a pretty good, it gives you a pretty good idea about how we're going to use these lines of best fit to make those predictions. Okay, so let's keep going. Once we've plotted a set of bivariate data, we can begin to see the relationship between the points. And we want to be able to determine whether the line that we've put through that set of data is actually a good fit of that data or whether it's a really poor fit of that data. So there's different ways that we can do that, or different ways that we can actually mathematically measure correlation. So one of the ways that we can actually measure correlation is by using these correlation values down the bottom here, and this is called the Pearson's correlation value. So with this particular value, if you have an R value that's equal to 1 or an R value equal to -1, that means that it's a perfect line. That means every single point exists purely on that line, and so therefore it's a really, really good model. On the other hand, if you have an R value equal to 0, that is really, really poor. So we have these models that sort of exist on this spectrum from terrible to absolutely perfect. So let's just go through. So the first one we've got here is the perfect positive correlation, and it makes sense that it's a positive correlation because this value here is +1. So it's a perfect correlation because it's got a value close to 1, and it's +1 because it's a line for every X value. As we increase across the X range, it's also increasing in the Y range. Now this value of 0.9, it's still pretty close to that perfect correlation. It's not exactly perfect. So what that means is if I was to draw a line through that, then not every point is existing on that line, but it's pretty close. Same thing with this low positive correlation. So as we're sort of going through, we're starting to see now that less and less and less of these points are on this line or can be described by this line. So it's not as great of a model as what I could really want it to be. This is obviously no correlation, and then going back the other way, we can start to see that these correlations down the bottom here are now negative. And what that means is every time that X goes up, Y is actually going down. And it exists on this spectrum of being really terrible to really, really good. And in fact, a correlation of -1 is actually a perfect negative correlation. So when we draw these lines of best fit, we can draw them by eye. Right, so literally all you're going to do is exactly what I just did before. You pretend that you are the Zen master and you just draw a line going through your data, and you've just got to make it like touch as much of the data as you can, right? And if you can't make it touch all of the points, then maybe try doing equal numbers of points above and below the line. Okay, so once we've done that, we know how to determine the equation of a straight line. So what we can actually do is we can actually work out what this line is going to be, and that's going to be some formula of y is equal to mx plus c. So once we've found that line, what we can actually do then is we can use that to make predictions. And there's two ways that we can do this, two ways that we can make predictions. So when I'm dealing with all my data, let's say I've only measured from this point here to this point here, okay? And so this is all of my data, and if I want to make a prediction that's outside of that range of data, that's actually called extrapolation. And I want to warn you, right? If you've only measured a particular range and you're extrapolating, it's actually a lot more likely that there is going to be some sort of error involved with extrapolation because you're trying to make a prediction outside of the data that you've measured. Okay, so just be very, very careful when you're trying to extrapolate data. The other more useful kind of prediction that we can make is called interpolation. And so what I mean by that is this is my range of data that I've actually measured, and I'm trying to find points within the data there. And that's going to be a lot more accurate because sometimes what can happen is like we don't always see what's going on at this point here. We could have a line that actually continues and looks something like this. Like we have no idea what it's going to look like. We could also have something that, you know, looks more like a wave. So it could look like that. Okay. So when we interpolate that data, we are a lot more confident about what it looks like in that area. Whereas when we extrapolate, we actually have no idea what that could actually be looking like. So that's why it's really dangerous to extrapolate. Okay, so here's an example. We want to predict the total number of people who have had coronavirus in Australia. So what will be the predicted number of people in Australia diagnosed with COVID-19 by the middle of May, given the following information? So I've got, excuse me, so I've got some data here just to show you. So this is a logarithmic scale, first of all. And the difference between a logarithmic scale and just a regular scale is that rather than adding the same amount each time, so rather than adding 10, so you have 10, 20, 30, 40, 50, we're actually multiplying by 10 each time. So it's going up 10, 100, 1,000, and then 10,000. So this is linear when it's on a logarithmic scale. So just be aware of that. Okay, so what we're going to do now, we're going to use this information to help us make a prediction. And we're going to be extrapolating information because I've only got 3 data points here. And let's say that February was month 0. So let's say t or time is equal to 0. Let's say this is equal to month 1, and let's say this is equal to month 2. Now, we're trying to determine the predicted number of people diagnosed with COVID-19 by the middle of May. So we're actually trying to find for the following month. So this is going to be extrapolating our data. And we've just spoken about the dangers of extrapolation. So this is not likely to be an accurate representation of the model for May. But what we can actually do when it comes to May, we can actually have a guess and have a check and see if our prediction was anywhere close to our actual value, which I have a feeling it probably won't be. I mean, there's different things that we can do as well that contains the spread or that can influence or increase the spread of this virus. And the Australian government seems pretty strict at this point in time about those COVID restrictions. So we've actually seen a bit of a decrease here in Australia, and I'm actually filming this video on the 24th of April. So I know, like looking back at this data, that it's actually flattened out even further from this. So it's actually not likely to keep going on this linear projection here. So just be aware of that because we are extrapolating data. All right, so this here is my number of people that have been infected. So let's call this my independent variable. So that's going to be called T, my independent variable. And this is my dependent variable. So let's call our dependent variable N for the number of cases. Okay, so now what we're going to do, keeping in mind that this is going to be on a logarithmic scale, is we're going to attempt to determine the equation of this line. So since this is going up exponentially, we're actually going to write this using an exponential function. So what do I mean by an exponential function? Let's just talk pretty quickly about this. So an exponential function has this general form. So I've got my independent variable, my dependent variable here. I've got my independent variable here as a power, okay? And that makes sense because this would be 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and so on. The other piece of information that I know is that this value a here, that's actually the value of the function when x is equal to 0. So in our case, we've actually got our dependent variable equal to 15. So we could substitute that 15 in there. This value b, that's our common ratio. Okay, so what do I mean by common ratio? I mean, what are we multiplying this number by each time? So just quickly having a look at this, 15 times by 20 is going to be 300, and then 300 roughly times by 20 again, actually, that's not a bad little fit there, is going to be about 6,000. So that's good. That actually kind of worked out. That's nice. So that means it probably is going to be some sort of logarithmic or some sort of exponential function. And so since our common ratio is 20, we can substitute that value in here now. Now what I want to do is I want to replace my dependent variable here with n, and I'm going to replace my independent variable with t. So let's rewrite this. So we have n as a function of t now is going to be equal to 15 times by 20 to the power of x. Now, because these are different bases, we can't multiply this. This is not 300 to the power of x. No, 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 no. Because different bases means that we cannot add the indices. Okay, so now what we're going to do, now that we've come up with this function, we're going to attempt to make a prediction for how many people are being diagnosed by the middle of May. And so to do that, we're going to substitute in t is equal to 3. So if I substitute 3 into my equation, I'm going to write the little 3 in the brackets here, and I'm going to pop the little 3 up here as well. So I'm going to just quickly pop this in my calculator and come back. So my solution for the number of people in Australia predicted to have coronavirus by the middle of May is going to be 120,000 people. Okay, and that's assuming that this is going to continue on in the same way that it is going on. And I think you can kind of see, especially if you're someone where post-May and you're looking back at this video and you're thinking, that is a ridiculous prediction. Because we can't predict the future at the end of the day. This is outside of my measured range. And so this value is actually very likely to be wrong. Now, we're sort of getting close towards the end of April here. Not quite, maybe like mid to late April here. They've taken a lot of precautions, the Australian government. They've shut down a lot of the borders. I know in Victoria and in Melbourne, like they're stopping people and they're fining people for non-essential travel and things like that. So in reality, in Australia, we're actually expecting this rate to slow down a lot. So this is probably not going to be a particularly accurate prediction. I'm saying that now. Let's pretend they open up all the borders tomorrow and then all of a sudden coronavirus is going to be everywhere again. And then that could be an underestimate of our value. But I think at this point, this is going to be an overestimate, or at least let's hope that this is going to be an overestimate. So now you can kind of see the dangers of extrapolating data, especially when it comes from real world data that has impacts outside of what we're seeing on the data. Okay, because we can't see all the political mess that's going on behind the scenes here. Okay, so how reliable is this prediction? Lines of best fit can be considered reliable when the number of data values is large, and we did have a whole bunch of points there because I took like 3 months worth of data there. So yes, I do have quite a large number of data points. There appears to be a strong correlation. I'm just looking at this. This to me does not look like it's going to be the best correlation because we do have quite a few points that are outside of this line. I think some sort of sigmoid curve would be a better description of this function rather than a linear one. And lastly, to make sure that this prediction is reliable, we have to make the prediction using interpolation, and we didn't do that. We did extrapolation. So my prediction is probably crap, to be honest. So how do we check if this correlation is actually strong mathematically? I might do another video on this. This is big brain math stuff. This is, we can do this using a table, but it gets kind of crazy. And that tells you how we get all of those values of R from before. So whether we had a strong positive linear correlation or a negative, strong negative linear correlation or anywhere sort of in between. But I'm not going to do that for this video because that stuff is big brain maths. That is the higher level stats stuff. Okay, so what I want you to do is I want you to have a go at question 1 and 2 here. And I'm going to come back with the answer for question 1, and you can check the answer for question 2 in your textbook. I was going to skip showing you guys this step, but I just thought actually, because you guys, I know aren't super familiar with Excel, but Excel is honestly probably my favorite computer program to use ever. It's like a big giant calculator. And for a maths teacher, that's like a very exciting thing. Anyway, sorry, a bit lame, I know. So the data below, the first question, what it's asking us to do is to construct a scatter plot of the data. Now you guys can go ahead and do this by hand. You don't have to do this in Excel, but I just want to show you how simple it is to do in Excel. So all I did was I typed my answers and I typed it using a vertical column rather than the rows that these have. And then all I'm going to do is I'm going to select my data. Oh, and something really important to note, I should mention, this row is the first row. When I transpose that, that should be the first column. Same thing here. This is the second row. So when I transpose that, that should be the second column. Okay, very important that we make sure that that's in order because this is effectively our X and our Y and we don't want to mix those up. So now I'm going to go insert a graph and I'm going to insert a scatter plot and then that's all you need to do. So that's my scatter plot there. Now what I can do is this program is really good because it can actually put in a line of best fit for you. So if you just go add trend line and then what we can do is just scroll down and we go display equation on chart. Now this is the R squared value. This is a different correlation value to the one that we've just looked at. So this actually squares the value. So this one doesn't consider whether or not the data has been accounted for in like a positive or a negative correlation. This is just telling you how strong the correlation is. So 0 is the worst and 1 is perfect. So you can see this has a value of about 0.9. So it's a pretty good fit, pretty strong correlation. And we can see from the graph that it's positive because as X is going up, Y is going up as well. So I'm just going to take this over now to the OneNote and I'm just going to paste that into my document there. Okay, so drawing a line of best fit. So I did that using Excel, but again, all you need to do is you can just get your ruler out, have a go and say, oh yeah, I'm going to try and catch as many of these points as I can. And if I can't catch all the points, that's okay. I'm going to go somewhere sort of in between. Okay. And then you can now determine the equation of the line of best fit in terms of those variables by just picking a couple of points in the line and using that method that we've used previously to determine linear equations. So that was a lot of information all at once. I'll show you. So I'm going to pick some nice points, and by nice points, I mean points that are on the line. So I'm probably going to pick that point there. So what point was that? That was, where's this one here? So that would be the point 12, 2. So I'm going to pick that nice point on the line. I might also pick this point because that's a nice point on the line. So what was that one? That one will be about 30 and about 5. So that's going to be this point here, 36, 5. And then I might just pick one more point on the line. I might just pick this one because that's sort of getting up to the top end now. You can see, by the way, as we get to the top end, it becomes less certain. These points seem to be going a little bit crazier as we get closer to the top. So that one's going to be about 70 something and about 9. Oh, yep, here we go, 67 and 9. So I'm going to pick those 3 points. So we only need 2 of these points to make a straight line. So I'm going to do that working off screen and come back. All right, so to quickly summarize what I've done, first things first, I determined the gradient. Now I can't see the y-intercept on here, so I went ahead and calculated the y-intercept by substituting in my points. And what I did was I used these 2 points to determine the gradient, and then I substituted in my third point to find that y-intercept. Now you don't actually need a third point to do that. You can substitute any one of these 2 points in, but the more points you incorporate, I'm hoping the more accurate this model is going to be. And so now I've got my value for my gradient and my y-intercept. So I've got y is equal to 0.125x plus 0.625. So if I was to extend this line out further, I would assume that that would go through about 0.625, and that looks pretty reasonable to me. Okay, so was that all we had to do? Yep, so we constructed the data, we've drawn in the line of best fit, and we've determined the value of the line. Now, the only downside with this is we can't see how well this line fits. But I'm going to make a video for you showing you how to do this in Excel and in Desmos, so keep an eye out for the next one, so modeling data with technology. Alrighty guys, a bit of a long video, do apologize, but it is a really interesting topic and it's something that I really enjoy, which is I think why I tend to harp on about it. Because everyone always asks me like, Miss, when are we going to use this in real life? And you know what, I've only ever been in like the maths and science fields, and so for me it's like, well, I use it all the time, so I can't justify it to you because I always use it. But you're not in the same context or the same situation that I'm in. So when I went through uni and when I was doing all my science degrees and stuff, we did a lot of this kind of stuff, especially because I did a chemistry degree and like we would be measuring different variables. So for example, we might be measuring reaction rate against temperature of a reaction, or we might be looking at like pH levels or something like that. And so a lot of those equations had really nice linear graphs, and a lot of the times I was actually getting very high R² values for my equations. And like it's a skill that I used a lot. So I can't really justify it to you if you're not going into like a math science space, I guess. But hey, at least maybe you got to use a little bit of Excel. I don't know. Anyway, I'll talk to you guys soon. Hopefully I will get to see you in a very, very short period of time and we won't be apart for too much longer. Okay, talk soon. Bye everyone.